Okay, so this is proof of Bourgain of the second maximal theorem. And I'm just going to recap a little bit about the proposed strategy we discussed last time. So remember, we're trying to bound these multiplicity functions, which are given by these sums of oscillating characteristic functions of delta annuli. And we want to form a bound for an arbitrary collection of circles. So here, all our collections of circles, remember, have delta separated centers, which lie in the bounded domain and have radii between 1 and 2. And our plan is to take our arbitrary set of circles and decompose it into two pieces. One piece, which is the C trans, consists of circles which interact transversely, and the other piece is complement, which is a collection of circles that sect tangentially. And for the transversal circles, we aim to get an improved L2 bound. So we already know that this L2 bound holds for an arbitrary family of circles without that delta the epsilon. So we're going to improve it a little bit by having this factor of delta the epsilon. And that improvement necessarily relies on the special structure of this family of circles. Okay? And complementing that, we're going to prove an L1 bound for the transversal circles, which again improves over the uniform bound. So this L1 bound without that delta the epsilon, so with the delta power on the right hand side.
You mean tangential?
Sorry, tangential, yes, sorry, tangential. Yep, this is, I don't know what I said, but I presume I said the wrong thing. so the tangential, for the tangential circles, we want to prove this improved L1 bound. So for any collection, we trivially get an estimate of the delta on the right-hand side, so we're going to prove that to the delta epsilon. Again, we have to use a special property of the transversal tangential circles to get this. Are there any questions about this before I get started? Remembering this vaguely from last time. Okay. So, and of course, once we have these two bounds, we can do an interpolation to get a good estimate for the whole. So let's start by discussing this partition. So throughout, I'm going to fix some exponents e to an epsilon, where e to is much smaller than epsilon, and epsilon is much smaller than 1. So probably we can take epsilon to be something like 1 over 100, and e to be something like 10 out of it. Okay. I'm going to construct a sequence of sub-collections of circles. So we're going to have C0, C1, and so on. This is going to be a nested sequence of subfamilies of circles using a greedy algorithm. To try to construct something that gives us the transversal collection. Okay, so how do we do this? Well, very, very simple. So we're going to start off by defining our initial set of circles just to be the whole collection. And then let's suppose we pass through a number of stages of this algorithm, and we've got to the J family. Okay? So suppose it can be constructed. And now we want to explain how to go to the next family in this sequence. So there's going to be a stop. We have this following stopping condition. So if for all circles in the J family, when we look at the set, which I'm just going to use this opportunity to introduce some notation here. So CJC, which consists of all circles C bar in CJ, which are close to being tangent to C, Most meaning this tangency function is less than delta 1 minus theta. So if this satisfies cardinality, this family of tangent circle is small, so okay, so we're going to have this weird looking signs that you might remember from the lecture ago. If it's small, and then the algorithm stops. Okay. So what's the idea behind the stopping condition? We have to cast your mind back a couple of lectures. So remember, we had this lemma that said we had an improved L2 bound if we have very few circle tangencies, right? And this stopping condition is saying, okay, for every single circle, if we look at the number of circles tangent to it, that's small, then we stop. So we're kind of stopping once we're in a situation where we get an good L2 bound, we have few tangencies. This is going to give us our this is kind of greedy algorithm construction, giving us our transversal set. Make sense? Yeah? No? Maybe? Okay. Right. So that's stopping condition. So what do we do? Well, otherwise it's going to exist some circle, which I'll call CJ, I guess, in the J family, which has many tangents, which is tangent to many circles. So such that the cardinality set of tangent circles to CJ is bigger than this delta to 2/3, it's 2/3 plus 1. Okay, so we don't stop, then we can find this guy, and we set CJ plus 1 with CJ with all these circles removed. Okay, makes sense? So if we find a circle that has many tangent pairs, we remove that circle and we remove all the circles tangent. That's our iterative construction. So it's just a greedy algorithm that's going to give us exactly what we want. Any questions about this? So of course this will terminate, because we're removing circles at each step, and we've only got a finite number to begin with. So it's going to terminate at some step J. Okay, so J is going to be the terminal step. And I'm going to define our transversal boundary to just be the terminal step. And as we've discussed, everything's set up so we have the transversal conditions. Okay. So just to reiterate this, so if we look at all circles in the transverse boundary, which are tangential to some fixed circle, and let's see the fixed circle, and then we'll look at all the C bars tangent to it, then this is all small. Okay. So that tells us automatically that we get this with L2 bound. Now, already got slightly hand. Okay. Right. So then like we have this with L2 bound, okay? With this family. This makes sense? So now the whole thing is going to boil down to the L1 bound. So let's just have a look at what our the structure of our remaining family of circles. So I'm going to define C tang calls to be the complement of the transversal family. And we can write this as a disjoint union of the sets that we remove at each stage. Okay, so in particular, it's a disjoint union of the sets, the set of circles in this jth step, little jth step, which are tangential to some Cj. Okay, and we can also understand, to help us see why this is a disjoint union, we can also understand these sets, families, circles tangent to a fixed circle as the circles in the whole family tangent to this fixed circle, but then we'll remove all circles from earlier families which are tangent to this fixed circle. Okay, so it has this disjoint structure. So this is just coming out of the algorithm. And the cardinality of each of these guys is quite large. So it's, well, it's given by this weird number in the algorithm, which is, we chose in order to get this matches with what we needed for the L2 improvement. Yeah. Okay. Great. So our goal now is to prove the L1, the good L1 bound, when we restrict our circles to one of these circle families following this disjoint union. Okay. And the point here is we can then sum using the disjointness of the Cj. So here it's important to work with L1 because we could just sum the cardinalities to the right side. Yeah? Make sense? So we don't have any control on the number or any reasonable control on the number of these families, but that doesn't matter because we can just sum the estimates. Okay? And I'm just going to abstract this a little bit so I don't have so much notation flowing around. But let's just abstract this as the following letter. Let me open myself some more space to write. We call this tangent case applies on one improvement. What I'll say, okay, we suppose is a collection of circles. Okay, satisfy the usual hypotheses of don't separate the centers and radii and the centers within these bounded region, such that there exists some root circle in our collection such that all other circles are tangent to it. Okay, and then secondly, this collection has a large cardinality by the bound we'll be working with. Then the conclusion is that we'll get a good element on that. This family. Okay. So this is what we're shooting for. So I'm just stating this lemma in order to isolate the properties that we're going to work with. Okay? And then of course all these CJ sets, CJ sets, satisfy the conditions that we can just apply to each other. Make sense? Okay. So now everything boils down to proving this last lemma. Okay, so that's what I'm going to spend the rest of the time doing. So let's start proof. And we're going to break it up into 8 steps, 8-step program to prove this down. Okay. So but a lot of the steps are very short. So don't worry about it. So step 1 is critical volume. So I'm going to look at this family of circles A according to the distance of circles from our root circle C0. Okay. So A0 is going to be all the circles whose distance from C0 is teeny tiny, and teeny tiny in our world is delta 1/2 here for some reason, but that's just super able to work with. And remember, the distance here is just the distance between the centers, yeah? And then we have BALs, which are the circles that get further and further away from C0. So it's 2CR minus 1 times delta 1/2. It's got some distance since C0 and transfer by 2CR. That's it. So it's the position of the distance. Okay. So now it suffices to show that for each of these AL sets, if we look at the corresponding multiplicity function in L1, I'm going to bound this by delta for 1 plus 2 epsilon and the cardinality of A. Okay. So once we have this, we can sum the estimates together trivially, and we'll pick up the number of terms in the sum. But there's only logarithmically, well, log delta the number of terms in the sum. Log delta inverse, yeah. So that means we only lose logarithm in delta, but then we can eat up that with one of these delta the epsilon powers. Okay, so that's fine. It's just diagonally backwards. Right. So that's our new goal. Okay. Probably these steps are some help with quite short, so now we move on to the next step. So this is to deal with the set taking a custom case. Is the set A0, okay? So we have to treat this kind of separately because this has a slightly different definition, but okay, I'm going to brush over this. This is easy. And we'll use the fact that the cardinality of A0 has to be much smaller than the cardinality of A, much smaller. Okay, so where does this come from? Well, here we're looking at circles whose centers are in this delta 1/2 distance from a fixed point. The centers are delta separated, so there can be only delta -1 such circles. Okay. But the cardinality of A is bounded below by some quantity in our hypotheses. So that means the cardinality of the A0 is much smaller than the cardinality of A. So you can just do a kind of trivial estimate on A0, and then when you pass the A0 to A, you get a gain from the relative cardinality. So that seem reasonable? So this is an easy and boring step. So let's briskly move on. Step 3. Okay. So step 3, I'm going to perform a partitioning of the L1 norm, and I motivated this at the end of the last lecture. Partition. So I'm going to fix L. Remember, L is the parameter dictating the distance to the centre and the distance between the centres. And I'm going to let rho be this 2 to the L delta 1/2, which is featured in our pigeonholing. And I'm going to choose kappa, be some parameters going to be delta 5 epsilon. Okay? So then I'm going to let sigma be some constant A1. So this constant is just an absolute constant times the product of rho and kappa. Okay, so just some parameters. And what I'm going to do is going to bound the L1 norm of the multiplicity function over AL. Well, bounds on right, but I'm going to split up the norm. So we're going to put part, which I refer to as local part, where the integration is over the sigma annulus around our root circle C0. And then we'll have the second part, which is just the integration over the complement. Okay, so the sigma is going to be bigger than delta. So it's quite a big fat annulus, yeah, around C0. And so strictly speaking, well, we should really do this with this. We should use the smooth cutoff. And I'll come back to this later, but for the purpose of this lecture, I'll just use a quick cutoff. Okay. And that's step 3, which is partitioning. So we've got these 2 separate parts that we're going to work with. Now we have step 4, which is to do with this local part. Which I already described what we're going to do with this at the end of last time. So now, what we're going to do, okay, so let's take this local part, where we're only going to consider the integral over this sigma annulus. And we'll trivially apply the triangle inequality over some of the circle around the norm. And now we remember that these chi wiggles are oscillating characteristic functions. We've killed the oscillation now by triangle inequality, so they just behave like characteristic functions. So now we can bound this by the sum of the volume of the section between this C delta and this C naught sigma. Okay, so we need to work out how big that is. So we did some because we did a bunch of trigonometry and stuff, or we talked about trigonometry last time. That's allowed us to prove these letters. So maybe I'll pull this down so I can discuss around it a bit more. So we're going to use this lever on the right here. This is giving us a bound for the volume between the intersection of two annuli, one of radius delta and one of radius sigma. Sigma has to be quite large, and our choice of exponents ensures that this is the case. Okay, so I won't go through that computation, but you can see that this sigma has to be quite large. And the idea here is, okay, so we're in this situation, the right-hand picture, so we've got our two circles, and we're going to fatten one up by some radius that's bigger than the tangency measure. So that means when it's bigger than the tangency measure, the fattened up annulus contains this whole arc. So it contains a whole arc of the circle. Yeah? And that's where this numerology comes from. Okay. So we just put this in. So we're going to get this delta factor coming out, and then we've got sigma divided by the distance between the centres. 1/2. But we pigeonhole, so the distance is just this fixed parameter rho. That's what the definition of AL is, right? So we pigeonhole, so this distance is fixed. And sigma is just rho times kappa. So this thing just becomes capital 1/2. Yeah, so we're going to have a bound delta times capital 1/2 times the cardinality of AL, which is divided by the cardinality of A. Okay? And kappa is just some power of delta. Okay, so okay, maybe I want to keep the AL for now to be a little bit pedantic. So I'll keep the AL for now. And we'll get a delta for the 1 plus. No, that's fine, it's fine. Go like this. About 5. That's 1 over 2. That's kind of to be able to put it down by delta plus the 1 plus 2 epsilon. Okay. So we get this that's about okay, is that right? Whatever, we get some improvement, which is the cap. So this part is pretty straightforward. So now we have to look at the. Are there any questions about this before we move on? Okay, so now I need to look at the non-local part. Fix under this. Spec 5. Non-local role. And the first, in order to analyze this, we're going to perform some trichotomy. Okay, go to the next step. So we remember the non-local norm. The norm of the complement of that. Okay, so I'll call this a non-local norm, but I'm going to put this in quotation marks because all norms are local in our setting. Okay, so I claim here that for all circles in AL, if we look at the delta annulus around the circle, this is going to be contained in some big fat 10 row neighborhood of our C naught. Okay, and this is pretty easy to see using the setup. So we just got to think about what's happening. These circles are both tangent and have distance rho from the center of C naught, which kind of forces them to lie in this this fat annulus. But let's just give a proof so we're convinced it's the case. It's straightforward to do. So the proof is followed. So remember, the distance, the sentence from C to C naught is bounded by rho. That's what it means to be an AL. Also, we have tendency is bounded by delta to the 1 minus eta, which is going to also be less than rho, because this rho is bigger than delta 1/2. Okay, this is from what it means to be an A. Okay, so then if I look at the difference between the radii of these circles, I can do a triangle inequality. So I can subtract off the distance between the centres. So R is the radius of C, R0 is the radius C0, X is the centre of C, X0 is the centre of C0. And then I'm going to what we're going to do, then I'm going to add the difference between the centres. And maybe I'll put an absolute value around that thing. So this quantity is exactly our tangency measure. This is just the definition of delta C0. Okay, and this quantity is exactly the definition of the distance, it's just the distance between the centres. Yeah? So the difference between the radii is going to be bounded by 2 times rho, because both these terms are bounded by rho. Okay? So now we know both the centres and the radii bounded by rho, which kind of means that these two circles are indistinguishable at the rho scale. Kind of motivates why you should be able to contain one in a rho annulus right here there. So, in particular, if we pick a point in the C delta annulus, we want to show it's in this fat annulus around C0. So then I'll be checking if it's in that annulus, where we have to look at the distance from the centre of the circle. This has got to be equal to the radius up to some error, which is allowed to be 10 rho. Yeah, so we want to show that this is bounded in absolute value by 10 rho. And again, I'm going to do a triangle inequality. So I'll split this up as the difference from y to the centre of x. And then I'll subtract to R. And then I'll add the difference between R and R0. And then I have the difference between x and x0. Yeah? So now all the pieces are in play. Because y is in the annulus around C, this is what it means. If this is 0 when we're in the circle around C, so this holds up to delta error. So the first term is bounded by delta. The second term is bounded by 2 rho, that's what we've already discussed. And then the third term is bounded by rho. Okay? So we can bound this to by 4, which is definitely bigger than delta. So 10 is a bit of an order. That makes sense? Okay. So we have this claim that all our central circles actually contain this really fat annulus around C0. So what I'm going to do is use this local property to pull out the volume. The flat annulus raised to 1/2 and raise the L1 naught to L2 naught. Okay. This is the 10 rho guy. So what's the volume of this 10 rho annulus? It's basically just rho, right? Yeah, it's just thickness. So now we get rho to 1. All good? Okay, so now we trade the L1 for L2, and we're going to use all these L2 gains to try and estimate this thing. Okay, so now we're going to perform this trichotomy that I mentioned before. So how does this work? So I'll break up the L2 norm in the usual way. So we're going to write this in terms of the L2 in a product. Maybe I'll square everything. Okay. So I'll write this in terms of the L2 in a product. And pull out the summation. So we're looking at all these in product pairings. C1 delta. These kind of wiggles associated with the different C's. And of course, we need to restrict the integration in the L2 norm to this particular set. We'll remember that we're working with this particular set. Okay. So now for every bit C1, I'm going to decompose the sum in C2. Okay, so first I'll get what I'll call a dyad C1, which is the diagonal terms. These are going to be all the C2s, such that the distance from C1 to C2 is small. And here small means it's less than this kappa parameter, which we've used before, so -1 times beta, where beta is our measure of tangency. So it's delta to 1 minus eta, which is appearing in all these, appearing in the definition of the A set. Okay, so it's a measure of tangency. Right, beta for them. Okay, then I'm going to have a tangent set. Let's say D1. These are all the C2s that do not lie, essentially they have, that do not lie in diagonal. Who are tangent C1 in the sense that this is a bit more space. The tangent C1 in the sense that this tangency measure is bounded by this kappa parameter times the distance between C1 and C2. Think of this as saying that the tangency is small. Okay. And then we've got the remaining set, which I don't need to define, this is just complement these two. So just to be clear that okay, well, so then we have the transverse there, which is just a complement of the union of both the previous sets. What does that mean? Well, it's going to be all the ones that lie to diagonal, which are not tangential. So this inequality is with this. Okay. So that's our these are our three sets. And we're going to estimate the terms in the sum when we restrict each of these sets. Any questions about this? Okay. So now we've got steps 6, 7, and 8, and 6, 7, and 8, one for each part of this trichotomy. Okay. First, we look at diagonal terms. This is going to be easy. Again, we're going to use the fact the cardinality of the set of diagonal terms is small. I'm not going to found by something that's relatively small. Okay, so this you can just estimate just as some Cauchy-Schwarz. Okay. Just, know, there are only a small number of circles that close to any given fixed circle. And then now we move on to step 7, which is a tangent term. This is the really the meat of the matter. Here, we're going to use what we know about clamshells from earlier. This is where we see this clamshell configuration coming in. So what I'm going to do is write out this tangent term. I'll give it a name, I'll sigma tangent. So we're summing overall C1, and when we sum C2, we're going to restrict only to the C2, which is tangent C1. Maybe I'll pull in the absolute opposites. So some of these are product pairings. And then we have this restricted product, which is important. Yeah. We're only taking away from this mechanics, okay? So what I'm going to do here is, so this is where we're going to use where we've removed that annulus. This is where this is important. So what I'm going to do here is, again, ignore the cancellation. These are bounded once you take absolute values to the basic characteristic functions of these circles, or these annuli. So then what this sum becomes, once we pull in the absolute values, is, okay, then we have this double sum. We have the volume of the intersection between C1 delta, C2 delta, and this complementary region away from this. Okay? Make sense? And here we use the fact that here we use this, the geometry of these tangential intersections to show that this is basically 0. So in particular, let's remember all the properties that we have. So we know in the setup that any pair C1, C2 formed from these ranges of summation, well, they're both tangent, both C1 and C2 are tangent to our fixed circle C0. So this is the setup for these A sets. Okay, we know that the distance is pigeonholed. That's the definition of the ALs. So it lies between rho and rho over 2. And then also we know more or less that the tangent, the C1, C2 are also tangent. Okay, so both circles are tangent to C0 and they're tangent with one another. And that's the definition of this A tangent set. So in particular, this plus beta is going to be bounded by. Okay, so this is removing the definition. What it means to be include the base we can bound. Okay. Right. So now we have to go back to what we discussed earlier in the week. So our second geometric lemma, which tells us, okay, so okay, so we have this big long statement that we'll just go through in detail, but we're in the setup, and we're in exactly the setup we're discussing. So we've got C1 and C2 both tangent to a fixed circle, and they have a distance about rho from the fixed circle, and then they're both tangent to each other. And we know that we can have these, if we have two circles that are tangent to some fixed circle, the only time they can be tangent to one another is if we're in a clamshell configuration. What clamshell configuration means is all the tangencies line up, they all occur in the same region, okay? And then we showed, if that's the case, if you take a sigma neighbourhood of C0, and this is a relatively, it's much smaller than a 10-row neighbourhood. If you take a sigma neighbourhood of C0, that will contain all the intersections. Okay? So this is our sigma neighbourhood of C0 containing all the intersections, which was our earlier geometric number. So the idea is if all these intersections have to occur in the same arc, okay, and that allows us to efficiently cover them all by this sigma. Okay, so what does that mean? It means that this thing's effectively zero. Okay, and because we're only, these intersections all lie in the C0 sigma arc. Okay, so we can just think of this term as zero. In practice, not literally zero because these are not literally characteristic functions, but it's completely negligible. So, okay. Any questions about this? Okay, so that leaves us with step 8, which is deal with this verse. Okay, so now we have a similar sum. Sum over the C1s, and sum over the C2s, and we only sum over the C2s, which is transversal to the row. And then we have some negative product values. Now, okay. So here, this restriction is going to hurt us a little bit, but in a way that I'm not bothered to go into much detail about. Okay, so what the idea here is the circles are transversal. So as we've discussed all the way from the outset, that we expect good bounds for the inner product pairings. That's the whole point of using this Fourier analysis, is that we get very good decay in the transversal case. So I'll just recall that. So if we have one of these inner product pairings, then we can always bound it by delta times 1 plus. Okay, so delta times some negative power of the distance between the centers. The scale of distance suitably. And then we have some term that's decaying rapidly. Depending on the measure of tangency. Okay? This comes from the Fourier analytic nature of this decomposition, the fact that these things are also there. So this is calculating the oscillation. So for us, this looks fantastic because if we're in a transverse case, this means this delta is big, wherever. This delta is big, well, it's bigger than this, whatever this is, and this, okay, I showed that this is fairly large. So that will give us the rapid decay. Okay? So this looks really good, and then once we've got rapid decay, we're done. But we can't quite use that because we've got this restricted region of integration. And the proof of this relied on using things like partial-Ernstine. You can't do partial-Ernstine when you haven't got the whole domain. But what we can do is just be a bit, a bit hard-working and just go into the proof of your self-estimate to show something still holds, even if we restrict the range. And that's what we get. It's the following. So, by analyzing the oscillatory intervals rather than directly using RL. If we look at this in a product pairing, we restrict the integration with working with, then we can bound this by something that looks the same. So we get the same decay in relation to the distance between the sensors. Okay. But then the estimate's weaker in two sense. First of all, we're only going to get a single power decay in the tangency parameter, transversality parameter, rather than rapid. And we also lose in the signal, which is quite natural, in the width of the annulus. Okay. So I'm not going to go through the proof of this because it's a bit technical, but this is based on oscillatory interval techniques. And you would expect to get a loss in sigma because, you know, when you, this is, oh, okay, so I should be a bit careful. And here we should really use a, this is where we should use a smooth cutoff. Remember I mentioned that earlier. So you should really work with a smooth cutoff in this setup in order to be able to differentiate the cutoff function. And when you differentiate the cutoff function, because it's width, it's, you know, you're moving something with sigma, you lose a sigma inverse. Okay. So so the moral of the story is, okay, we get a weaker decay in the transversal case, but this is still good enough. And you can complete the argument. So this part of the argument is very much ties into our earlier paradigm that we can always just restrict to tangential cases, because when the transverse, you get the rapid decay from the oscillation. So that's all the steps of the proof. So this is quite a different, well, I mean, it's a reinterpretation of what you'll find in the paper, so it's presented a little bit differently, we'll get to him, but this is the essence of the argument. So, yeah, done. Thanks.
Thank you, Jonathan. Any questions? Comments? Everything clear? All right, you can also ask questions later. So let us thank Jonathan for the whole cycle of lectures.